So we are entering this very important chapters on the energy principles. So please be careful. This is something that you probably have not seen before. So our objective for this chapter is trying to use some sort of energy concept to calculate deformations of any structure. But the structure so far is still confined to determinate structure only. But later on, we'll try to expand and get into indeterminate structures using also energy-based approach as well. Okay, so we are analyzing the performance of deformations of a structure under loading. Quickly sit down. So let's take a truss structure as an example. So I apply a loading on the truss structure. I just wait. Otherwise, you'll be lost in a few minutes. Concept is only a few minutes. Okay? You find your favorite seats? No? Okay? Okay, so here I use a truss structure as an example. I apply a loading on it, and the structure will be deformed. We always magnify our deformations. Otherwise, I cannot explain to you. The deformation is always very, very small, to limit ourselves to the elastic range. Okay, so we are interested in finding some sort of deformations. Now, for truss structure, we are looking for displacement. For beam and frame structure, we are not only looking for displacement, we are also looking for rotation angles. Okay, so now, do you know how to calculate a work done by external force? This probably has been introduced in physics, in fundamental physics or applied math. So how to calculate work done by external force F? So basically, it's force time deformations. But you have to integrate from 0 to the final deformation state. So it's work time deformations. Okay, so basically follow this relationship. Now, depends on how you apply your loading. Then this work can be obtained in two different formats. Depends on how you apply the loading. Bro, don't look at your phone. I'm just trying to be nice because I'm telling you that only a few minutes. If you missed it, it'll take you a long time to come back. Okay, so this is work expressions done by the external force F. As I say that the work is integration of force times d displacement from 0 to the final displacement. And I say that this integrations, the format, the explicit formulation, depends on how this F is applied. Okay, so for instance, if I apply the loading like that, linear relationships between force and deformations, right? So this work can be derived because F and delta F is related to a constant line. So the work done by this F force there is simply just the area underneath the F delta functions. Okay, so explicitly it's like that. I bet you have seen that. So this kind of work is applied gradually onto the structures. Right. Now, there's another type of loading that can be applied to the structures. So if I apply the loading suddenly, like that. So I apply the loading immediately with this amount. Then as it goes on, the deformed shape comes out. And the work done by this force is the area underneath this curve. So that is the work here. So it tells you this fact. The work done by the external force depends on how you apply the loading. So repeat, if I apply the loading slowly, let's say that this is structures. I apply the loading slowly applying it, and then it starts to deform following this linear functions. Then the work done by this force is 1/2 F time displacement. But if I apply the loading suddenly, like that, then the work done by the force is F time the deformations. So it tells you the ways you apply loading actually will decide on how much work you put into the structures. Okay? Now, this is so-called quasi-static, slowly applying the loading. You don't create any extra impact into the structures. Now, this sort of force applied usually implies that you're hitting the structure, So as a matter of fact, the structure will be subjected to deformation as well as some sort of vibrations, right? So this is so-called constant instant force applying onto the structures. So anyway, this is the work done by the external force. So the question is, where does this work go? Now, if you have studied physics, you know that work cannot just disappear. They have to go somewhere, right? So actually, what happened is the work done by the external force will go into the system and store inside the structures in the form of so-called strain energies. That's why you study strain energy in mechanics of materials, right? So because the work done by the external force is saved into the structure in the form of strain energies. So how do I see that? Now, this is a work assuming that you're applying the force in a very slow motion. So the work is 1/2 force time deformations. So this work is going to get into your structures and store in the form of strain energies. Okay, so how do we explain this? So here, I have a truss structures under loading of F and deformed. So because the structure deformed, each individual component also deformed, all right? But before that, this force is going to carry into the internal components, through equilibriums. So all this force component will carry some sort of force. All right, so let's take this small element, this one of the elements out and see what happens inside the structures. So this force is the internal member force due to the external force F. So because of this presence of internal force, the component will be under some sort of tension or compressions. So you can imagine that this component is going to either be compressed or be elongated because of this force. Okay, so after the loading appears, the component will be subjected to some sort of deformations. We call it DI. It's called member deformations. Okay? So the strain energy stored inside this member is equal to 1/2 internal member force times the member elongations. All right? Just like external work, the internal force will also do work. All right? This work is passed on from the external work. And we call this strain energies because it's related to the deformations of a members. So this is called strain energies. So according to the conservations of energies, now the total strain energy will be, of course, adding up all components. So this is a total strain energies. Now, according to the energy conservations, the work is going to be transformed into inside the structure in the form of strain energy. So here, it's called W equal to U. So equation goes like that. 1/2 external force times the corresponding deformations, external force, corresponding deformations. So this is the external work. And this external work is going to pass into the structures, inside the structures, start to deform the internal members, and internal members is going to save the energies in the form of strain energies. So here, this is strain energies. And summation indicating that you need to sum up all components, because all components will be subjected to some sort of internal forces. Okay, so don't forget our objective is trying to find deformations, displacements. There, we try to find that. As it turns out that we cannot directly find this from these equations. We cannot still. But this is a start. Now, we established the work and energy relationships between loading and internal structures. Okay, so what actually can be used to calculate is actually one principle after that is called virtual work principles. Virtual work principles. So this is what happens. So imagine that I have a structure putting on a force, and the structure is deformed and achieve equilibriums. Everything is stopped. The loading has been stopped. The deformation has been stopped. It's called equilibriums under loading. So we say that we want to throw in some sort of disturbances. Disturbances means that you try to move the structures away from the equilibriums, right? So this kind of disturbance is imaginary. It's not real, right? So mathematically, you want to disturb the structures a little bit away from the equilibrium and see what happens. Okay, so I want to perturb the structures. Now, basically, there are many ways you can disturb the structures away from its equilibriums. For instance, I can artificially, assuming that a deformation, additional deformation has been injected into the structures. So this is imaginary deformations injected into the structures. When you do that, you make sure that you're holding all the forces as constants, right? So you artificially inject some sort of imaginary deformations into the structures and then see how it performs in terms of work and energy relationship. Okay, so this kind of artificially assumed deformation is going to affect the internal members to deform as well. All right? So the internal member will be coming in with compatible deformations, compatible to the assumed external deformations. All right, so this kind of disturbances is performed, as I say, under the assumptions that during these disturbances, all the other conditions remain constants. So the force remain constant during you apply this kind of disturbances. All right, so the work done under this imaginary disturbances will be the area underneath this line. So here is the imaginary work that you introduced by disturbing the structures. Okay, so you will create the so-called virtual work into the system. So this virtual work is the real force times the imaginary displacement. That's one type of disturbance that we can create. Now, another type of disturbance we can create is to introduce imaginary, artificially imagined force into your system. So, for example, I can introduce additional force to go along with this one. So the effects of this additional imaginary force is going to carry into the internal members, creating the internal imaginary member force as well. So here, this is imaginary additional member force created because of that. You can obtain that through equilibriums, of course. Okay, so what is the work done under that scenarios? Now, the work done under that scenario while holding the other factors constant is simply just following this line, holding displacement constant, increasing force, so following that line. So the work done by that imaginary force will be this area. So that is the imaginary or virtual work done by the imaginary force, delta F. So this is imaginary, and this is real. OK? So this is the work part. And then we have the strain energy part, of course. So the work, the imaginary work or the virtual work created by your assumptions is going to, again, save into the structures in the form of strain energy according to conservations of work and energy principles. So simply put it like this. So this is a virtual work. It's going to save in terms of virtual strain energies. And if I follow the first approach, holding F constants, disturbing the deformations, then my delta W, delta U relationship is like that. So for those factors that without small delta in front, that means the real conditions. For those with a small delta in front, that means the imaginary, a virtual system. OK, so that's the first type. That's this type. The second type is now I'm holding deformation constant while imaginary inject some sort of force in it. So that follows these equations. OK, so we are talking about imaginary now. Imaginary is something that you can create by yourself, mathematically created scenarios. OK, but you say that I still cannot see how I can use this to calculate my deformations. So here, next. So we'll be using this relationship in this course to calculate deformations. So we'll be following the second formula here. So the second formula here is actually called complementary virtual work principle. To be precise, it's called complementary virtual work principle. While the first one, the first equation, is called original virtual work principle. So this is the original virtual work principle. This is the complementary virtual work principles. But the name is too long, so usually people don't make strict distinctions between them. So strictly speaking, we should call this complementary virtual work principle. But more and more people decided not to make a distinctions. Just call it virtual work principle. So this virtual work principle we'll be using in this course will be assuming that I inject some sort of imaginary force into my structures and then study what is happening between work and energies. OK, so this is what I just explained. All right, so here is how we can use it to calculate. So imagine that I have a structure under loading, F. I want to calculate displacements there. So this force is going to carry into the structures. We can obtain the corresponding member force through equilibriums. So now I artificially inject an imaginary force in it. This imaginary force I call delta F. So basically, this delta F is going to create additional member force called delta small f. So I'm following this virtual work principles, delta W equals delta U. And this is the equation I'm going to use. OK, so the virtual work principles say this. Now, this is a principle, but I'll show you how you can use the principle to calculate in the next slide. So it says this. The complementary virtual work done by external virtual force system under the actual deformation of a structure is equal to the complementary strain energies done by the virtual stresses under the actual strains. Can you understand? You understand every word of it, right? But you don't understand what it means, right? So complicated. All right, I separate the colors for you. Hopefully you can understand a little bit more. So there are basically two worlds that we are talking about. One is called real world. The other is called virtual world or imaginary world. So the real world, I use blue color. Blue colors. The imaginary, I use green color. So from these equations, can you highlight which are greens and which are blue? So I highlight for you. This is virtual, imaginary. This is virtual. So from here, I can obtain this. This is equilibrium. So these two are virtual. So what are reals? Of course, our objective is to calculate deformations, which is real deformations. So this is a deformation that we want to calculate. So this is real. Also, this is real. The internal member deformation is real. So because of loading, you have internal deformation, so that is also real. So the statement just states that you have this virtual force times the actual deformations, so that's called complementary virtual work, is equal to virtual stress times the virtual strain, integrate for the whole volumes, and that gives you the complementary virtual strain energies. So this is complementary virtual work. This is complementary virtual strain energies. So that's what the virtual work principle is defined. Okay, still not clear how we can use this. So next is further explanations how we can use this to calculate. So basically, you have two worlds going on here. One is a real, the other is virtual. So this is real, this is real. This is virtual. Force, these two are forces, right? So according to linear structure, we can do superpositions. All right? So we can do superpositions. One on the real and the other on the imaginary, and then superimpose them. So this is a real system. This is the imaginary system. All right? So I want to find this. I want to find this. But I can find, I don't know how to find this, but I can find this f, and I can find this small f through equilibriums, no problem. I can also find this if I give you that through equilibriums. So there are two equilibrium analyses. One is from here to there, the other is from here to here. Two equilibrium analysis. Okay, so comes down to how we use it. Okay, so we can do it like this. Usually people assume that this virtual force is coming in with a magnitude of 1. Dimension is not important because dimension here will be canceled by dimensions there. So dimensions, the unit is not important. But the magnitude, we can assume this to be 1. And you can do equilibrium calculations and find that one. Okay, equilibrium. So these two are determined. Now, how about di? If I find di, then the only unknown will be delta f. So the only obstacle for us is to find di. Di is a member deformations. So member deformations for linear structures, for truss structures, is related to the internal member force. So member deformation is equal to FL over EA. All All right, so you can substitute FLE over EA there. And the only things that you need to find is F, internal member force. So this internal member force can be obtained from equilibrium analysis. OK, so that seems to be done now. So that's the final format that you can use to calculate the truss deformations. So here, I put down 1, which is a so-called dummy force, dummy imaginary force. And this is the real deformations that we are calculating. And this is the virtual force created by this dummy unit force. And this is the real internal member force times L over EA. And that is it. You can use this formula to calculate the deformations, delta F. Is it OK? It seems like a magic, huh? OK. So this is what happens. Now, what if I want to find deformations there under such a loading? Just now, I'm looking for deformations together at the locations of the force, right? So it works like that. So now, what if I want to find deformation at other locations? Let's say here. All right, so analyze this. This external force is going to create internal member force, Fi. So they goes together, right, through equilibriums. So this force create that internal force. This is real scenarios. So this F is going to go here. This is a real force. OK? How about the imaginary force or virtual force? Well, the virtual force pretty much depends on which or what deformation you're looking for. If you're looking for deformations there, then you need to put the virtual force there. Because together, they create virtual work. Together, they create virtual work. So with that understanding, then you apply virtual force 1 there. And then figure out what is the induced internal virtual force in the members due to this force. What is that? So this force can then be put into this and then calculate it out, come out with delta F. So the lesson here is, depends on what you're looking for, you need to apply your virtual force correspondingly. Right. A lot of people cannot get that because they don't understand where this virtual work principle is coming from. All right, good. Now, we can handle much more than just loading. We can handle temperature and misfit, settlements, etc. We can handle a lot of different scenarios using the same principles. Let's say that I want to handle temperature effects. Same equations. This is virtual work principles. Now, imagine that I have one of the members subjected to some sort of temperature changed. Now, if temperature, wait, go home to sleep. You too. Wait, 流晒口水. Go home to sleep. OK, so temperature change. If there's a temperature increase, then you know that the member is going to be expanding. If there's a temperature decrease, then the component is going to be contracting. So imagine that you have some sort of temperature change for this particular component. Imagine that the structure will be deforming because either this member is elongated or contracted. So can you find deformations at any arbitrary point of the structures? So the answer is yes, we can use the virtual world principles to do that. Hey, you wake up and you play foam. Hey, no? PowerPoint, okay. PowerPoint is here. Don't trick me. Okay. All right, so how do we use this? Am I speaking a monotone voice? Make you sleep? Wake up. Okay. All right. Here. Now, I have this temperature change. I want to calculate the deformations there. So what is real and what is virtual? What is real? What is virtual? So this is real, and this is real. So this delta T is going to go directly into di through the thermal equations. That is assuming that the whole structure is determinate. So only for determinate structures, the component expansions or contractions will follow this simple formulas. If this is indeterminate, then it doesn't work that way. Okay, so this temperature change goes through the thermal equations going into the component expansion or elongations. So that is real. What is virtual? Virtual is here and there. So this depends on what you're looking for. If I'm looking for deformations there, then I just put a virtual force there, assuming the magnitude is equal to 1. And that virtual force is going to carry into the structures through equilibriums and then obtaining this member force, virtual member force. So that virtual member force is going to get there. So as a result, you just do that operations, and that is it. You can calculate these values based on these equations. Misfit. Hey, I cannot. Hello, gentlemen. Hey. I keep telling you, if you feel sleepy, don't come. Go to the library. Library is for that. Okay, misfit. Now, what happens if I have one of the members, either it's too long or too short, or two members, one is too long, one is too short, and what happens? That's called misfit. So let's say that I have this member too long, and I force it in, right? Imagine that this member is too long, but I force it to connect. So because of that, the whole structure is going to deform. So can I calculate deformations anywhere on the structure? Okay, so can I calculate that displacement? So what is real and what is virtual? So this is real. That is member deformations. Go straight to that. That is real. So virtual, because you're looking for that deformation, so you apply a dummy unit force there. So that is virtual. And that virtual force is going to carry into the member force through equilibriums and get into that part of the equations. And with this two, then you can calculate delta F.